Okay, good. So the last thing that we need to show is that when you do rotation estimation on R, which has these planes of rotation, you plug in this as your starting state. The net result is as though like you picked one of these planes with equal probability, 1 over L, and then you gave the output of rotation estimation for that plane, which is, J over L times tau. And that's like the clue that finally you get in factoring that helps you discover L. So let me write that fact down. This is really the final theorem. With this start, rotation estimation outputs the so-called clue. Each of the rotation angles K over L tau with equal probability. Actually, strictly speaking, if you remember, rotation estimation algorithm can occasionally fail. It only works correctly with overwhelming probability, but okay. It's like with probably 1 over L, you get the output of rotation estimation as if you'd had a vector in the plane that rotates by this, and then with overwhelming probability, it correctly prints out however many digits you want of this. Okay, so this is the last thing we got to prove. So now I'm going to do a little bait and switch on you. It's a little bit cheating, but it's not really cheating. But to prove this, there's going to be some notation. It's going to be a little bit notationally laborious. And so then if we do this in the exact setting where these are the angles and these are the basis vectors and they have all these symbols in them, it's going to be a little bit tedious. So what I'm going to do is do the analogous theorem in a slightly simpler setting where there's less notation. And that will give you, the idea underlying this theorem. And then, you'll just believe this theorem. So again, what's going on? If you think about it, rotation estimation, how does it work? It takes a vector, that's the starting vector, and it does a bunch of different rotations on it. It rotates by theta, and then it rotates by 10 theta a bunch of times, and 100 theta a bunch of times, and 1,000 theta a bunch of times. And all the while it's doing this Hadamard test. This Hadamard test takes qubits in a vector state, and it does the rotation on them. But it uses this extra qubit in such a way that you can kind of compare the initial vector with the new vector and get a signal about how much the rotation angle is. And you do that hundreds of thousands of times, and eventually you get enough signals about the rotation angle that you figure it out. But the main thing to have in mind is that rotation estimation takes in qubits in a certain state vector, and it's just always rotating them a bunch of times within that plane of rotation. And as we saw, this is a very important feature that after you did one little Hadamard test in rotation estimation, the new state was still some vector in that plane of rotation. Because remember, we focused on this fact that we don't know how to make state vectors in the plane of rotation. So if we're given a starting one, we kind of have to not lose possession of it. We can rotate it around this plane, but we have to not destroy these qubits because we'll never get a state vector in the same plane again. Okay, so just the picture you have in mind is this rotation estimation subroutine. It's constantly rotating this state vector around these planes of rotation. So in this scenario with our particular R, we have these 2 times L planes of rotation. They're all perpendicular to each other, and they're spanned by these these 2 vectors, and well, this vector in the perp one, this vector in the perp one, this vector in the perp one. And I would like just to describe the exact same picture geometrically, but with way less notation. So that's what I'm going to do. And then I'm just going to tell you that it's exactly the same thing geometrically, just kind of without so much notation. Okay, so this is my long apology for why I'm going to pull this kind of bait and switch on you. So let me say this bait and switch now. Okay, so for simplicity, let's imagine that L is 4. Okay, just like I'm also going to fix a particular value, concrete value for L, just so that we don't have so many symbols. And we have 4 perpendicular 2D planes of rotation in our world. So these planes of rotation, which we'll now just call P0, P1, P2, and P3, are the simplest possible ones. R rotates R. P0 is just going to be the span of 0, 0, 0, and 0, 0, 1. And the rotation angle for this plane, I'm just going to call it theta 0. Okay, so instead of the two vectors being like SW 0 over L tau and SW 0 over L tau perp, let's just say it's this one and this one. Okay, and these are two perpendicular vectors in 8 dimensions. And we'll say that P1 is the span of 0, 1, 0 and 0, 1, 1, and that the rotation angle for this plane is theta 1. So you should really kind of focus on these first two coordinates. And P2 is the span of 1, 0, 0 and 1, 0, 1. And the rotation angle here is theta 2. And the last one, P3, is the span of 1, 1, 1, 0, and 1, 1, 1, and has rotation angle theta 3. Okay, so what I'm trying to say is instead of this complicated situation, let's just think about this situation. We have 4 mutually perpendicular 2-dimensional planes. The span of these two, the span of these two, these two, these two. These are 8 perpendicular vectors, so everything is perpendicular. And we'll just say the rotation angle here is theta 0, theta 1, theta 2, theta 3. And we're going to set up the analogous situation with start, where we're going to have the start vector, which is another 3-qubit state, which is an equal superposition of all of these ones, of all these first ones. So we're also going to imagine that start is just square root 1 over L, which is 4 in this case, times 0, 0, 0, plus square root 1 over 4, 0, 1, 0, plus square root 1 over 4, 1, 0, 0, plus square root 1 over 4, 1, 1, 0. Okay, so again, we're just going to imagine that it's the equal superposition of these. Okay, which is exactly analogous to this start being an equal superposition of the first basis vector in each of the planes. Okay, so what I'm trying to tell you is this picture is exactly analogous to this picture with less notation. So we're just going to prove the analogous theorem for this and be satisfied. Okay, so what is the analogous theorem? It's that in this simpler setting, if rotation estimation is performed on this start, each of theta 0, theta 1, theta 2, and theta 3 is output with equal probability, which is 1/4 each. Okay, so we're just going to prove this in this setting, and that will convince us of the first thing. Okay, and once we do that, we'll finally pat ourselves on the back and have factored. Okay, so in order to do this, I need to remember a little bit about how rotation estimation works, but not too much. Because remember, when we finally finished rotation estimation, we were like, let's never think about this again. Let's just kind of remember in a black box fashion how it works. We'll have to think about it a tiny bit again. So now I'm going to prove this proof of the analogous theorem. So proof of star. So let's remember a bit about rotation estimation. So how does it basically work? Okay, so remember, actually it does a ton of Hadamard tests with angle theta, and a ton with 10 theta, and a ton with 100 theta, and 1,000 theta. But remember, one thing that we thought about there was we could make all the new qubits you need for the Hadamard tests, and do all the unitary parts of the test, and just measure those qubits at the end, rather than as we were going along. So we're going to use that here. So it kind of does new qubit. I mean, you'll have to go back to lecture 21 if you forget this stuff, but D1 through dm for, I don't know, m equals order n. I called them data qubits. Okay. And then, you can think of it does one enormous unitary, which I'll call capital U. But this is basically the whole algorithm in some sense, on all the qubits, on A1 through A n plus 1. In our case, this is just 3, together with the data qubits. And then now it can finally extract. So it extracts the data qubits, gets all the results, and then some classical algorithm takes the results and processes them and figures out all the estimates and puts them together and outputs the answer. So it takes the readouts and outputs, theta hat, which is its estimate. And the point is that if the initial state of the qubits was exactly in the plane of rotation by theta, then this would equal theta with all the digits of theta with high probability. Okay. But now we have to analyze what happens if we do this algorithm where the initial qubit state is not just in one of the planes of rotation, but it's this equal superposition of things in planes of rotation. Okay, so we're just going to kind of imagine following this algorithm, but when we're in a superposition. And it's kind of remember way back at the beginning of this class where we talked about how one thing that's sort of cool about quantum computation is you can take any classical algorithm and make quantum code for it, and then you can make an equal superposition, the uniform superposition of all inputs, run the algorithm, and you'll kind of get an equal superposition of all input-output pairs. And naively, people are wow, quantum computing, it found all the answers in one shot, but you get only an equal superposition of all the input-output pairs. And we said that well, now what are you going to do? You could measure, but if you measure, you'll just get a random input-output pair. And a random input-output pair kind of sucks because you could have just picked a random input yourself and computed the output. So we're oh, this seems like a great power, but we don't really know what to do with it. And we started doing I don't know, Hadamard transform tricks and all sorts of stuff. But we're kind of exactly in the same situation here, where rotation estimation is a little bit more complicated because it's not a classical algorithm, it's a randomized quantum algorithm. But basically, it takes an input and computes something. And now we're using this quantum superpower to apply it to all possible inputs in superposition. And then we're going to kind of measure. And then it's we say to ourselves, unfortunately, we only get a random answer. But actually, in this context, a random answer is all we're hoping for. A uniformly random answer, that's what we want. So what is going on here is kind of this basic quantum thing of computing all the answers in superposition and then measuring, but only getting a random one of them. Okay, so that was a little philosophical tangent.
Bye.